Salam and welcome everyone. So we're going to be working on the question on the screen that says, by how much does the chemical potential of copper change when the temperature exerted on a sample is increased from 100 kilopascal to 10 megapascals? Take the mass density of copper to be 8,960 kilogram per meter cube. So this question again is saying by how much does the chemical potential change? So we already know since we're doing a question that involves calculation, the best thing is for you to read the question properly and write out the parameters. So they said, by how much does the chemical potential change? So we have by how much, we have chemical potential, we have change. So what you're asking us to look for is just the change in chemical potential. That's actually what they're requiring us to solve for in this question. When the pressure exerted on a sample is increased from 100 kilopascal to 10 megapascal. So when there is an increase in pressure, you already know that there's going to be an initial pressure, which they've told us is 100 kilopascal. And of course, you know what kilo is. That's the same thing as 100, right? Times 10 raised to the power of 3 pascals. The kilo is times 10 raised to the power of 3. Okay, it's increased from 100 kilopascal to the final pressure of 10 megapascals. And again, what is mega? Mega is just times 10 raised to the power of 6. So that's 10 times 10 raised to the power of 6 Pascal. Take the mass density of copper to be 8,960 kilogram per meter cube. So the mass density, so the density, mass density, whatever you want to call it, is 8,960 kilogram per meter cube. So this is the information we have. Now, in this question, we can see that the pressure changes. And whenever we have a change in chemical potential with respect to pressure, we end up with this particular formula. So the formula ends up becoming, okay, the change in chemical potential is equal to the change in pressure times the molar volume. So this is actually the formula we're supposed to use. This is the formula you get whenever you want to see the change, whenever you want to solve for the change in chemical potential with respect to the change in volume. Sorry, with respect to the change in pressure. So change in chemical potential with respect to change in pressure is this formula that you're going to use whenever you have questions like that. So of course we know what molar volume is because we've been doing a lot of calculations and a lot of physical chemistry. Molar volume is simply volume divided by number of moles. So that is basically what molar volume is. So I don't want anyone to confuse that molar volume with volume. So now we see now from our question that the change in chemical potential, which is what we're looking for, right? But then we have to figure out what the change in pressure is, as well as the molar volume. When we have both of them, we can times it or multiply it by each other to be able to get the what's it called, the change in chemical potential. So yeah, so to do that, let's first of all start with the change in pressure. So change in pressure is just simply P final minus P initial, and in this case, we know our P final to be 10 times 10 to the power of 6 Pascal, same thing as 10 times 10 to the power of 6 is just basically 6 zeros more, okay, Pascal. Then minus P initial, which is just simply 100 kilopascal. So this is just going to be 100, okay, and then kilo is 3 zeros, so times 1000. So Pascal. So basically 100 kilopascal is 100,000 Pascal and 10 megapascal is 10 million pascals. So change in pressure ends up becoming 9,900,000. So it ends up becoming 9.9 million pascals. And let's not forget what Pascal is. Pascal is the same thing as Newton per meter squared. So we can say change in pressure is also 9,900,000 Newton per meter squared. So this is this part. Now we have to switch to determining what molar volume is. Remember what I said, right? Molar volume is the same thing as what? Volume divided by number of moles. But in this case, in the question, we're not given volume, neither were we given number of moles. Sorry, not moles, number of moles. But one thing we're given is the mass density of copper, right? That's the only other information we have that could potentially help us. We're given the mass density to be 8,960 kilogram per meter cube. What this is telling us is very simple. We remember from our physics, science, chemistry, high school, part of your college, even primary school, sometimes we teach you density. We remember that density is equals to mass over volume, right? Density is equal to what? Mass over volume. So this is mass, this is volume. But here we don't have mass, we don't have volume, but we have density. But one thing we can do, because we know that we're looking for molar volume, and we can find a way to manipulate this formula for us to get mass divided by number of moles and volume divided by number of moles. What this is saying is that we're just going to divide this fraction here by number of moles. We're going to divide the numerator, which is mass, by number of moles, and the denominator, which is volume, by number of moles in order for us to get it. So what we end up with is going to be molar mass divided by molar volume. So density can also be seen as, very important, you guys, mass density can also be rewritten as the molar mass divided, you guys, molar mass divided by what? Molar volume. So when we do that, we can basically work with what we have. We can easily find what the molar volume is. Rewriting this formula in terms of molar volume, we end up with molar volume is equal to molar mass divided by density. And you may be wondering, well, we were not necessarily given the molar mass. So how do we go from here? It's not a big deal. It's not a big deal. Look at the question again. The question told us we're dealing with copper. Whenever you have the identity of whatever you're solving for in a question, you can always determine the unique properties. An example of a unique property of copper would be its molar mass. You're always gonna have the exact same value, provided you know the identity of an element. You automatically know the molar mass, right? So now we're gonna work with this. We're gonna work with this information using like the molar mass. So again, molar volume is what? Molar mass divided by density. We know the molar mass of copper to be 63.55 gram per mole. And we know the density of copper in this question to be 8,960 kilogram per meter cube. Now we've run into a problem here. In this particular question, we cannot proceed because we have a situation where the molar mass is in terms of grams and the density in terms of kilograms. So the best thing we have to do is actually either convert from grams to kilograms or kilograms to grams. So I am going to instead go from kilograms, right, to grams. So I'm going to work on converting this one from kilograms to grams and insert it back into the equation so we can actually do the calculation. So anyways, 8960 kilogram per meter cube. We want to make it to become gram per meter cube. So to do that, we're just going to do calculations, unit conversion. So 89 kilogram per meter cube times, so I'm using I believe it's dimension analysis, it's called 1000, sorry, divided by, you're going to have kilograms at the bottom here. We're going to have grams at the top here so that we can actually cancel out the kilograms. And we know that 1000 grams is going to give you 1 kilogram. So that's just basically what's required here. We cancel out the kilograms. So 8960 times 1000 gram per meter cube is going to be the full answer. So you're just going to have 8960 times 10 raised to the power of 3 grams per meter cube. So we can insert this information back into this equation. So rewriting the equation to solve for molar volume, you have molar volume ends up becoming molar mass, which is 63.55 gram per mole, okay, divided by 8,960 times 10 raised to the power of 3 grams per meter cube. So, alhamdulillah, thank God, we can actually just cancel out stuff. We can cancel out the grams. Yeah, 63.55 divided by 8,960 times 10 to the power of 3. Put that in your calculator, you end up getting the molar volume to be 7.0926 times 10 raised to the power of minus 6. And you have, of course, 1 over mole. divided by 1 over meter cube is the same thing as just saying meter cube per mole. So the molar volume is actually going to be 7.0926 times 10 raised to the power of negative 6 meter cube per mole. So that's basically what the molar volume is. And I want to quickly mention something. We've done some calculations, but I don't want anyone to get tired and confused. What we've just simply done is to determine the change in pressure, answer, as well as to determine the molar volume. We actually haven't found what we're actually supposed to look for, which is a change in chemical potential. So we can now write the change in chemical potential, which we know to be change in pressure times molar volume. So we can have change in chemical potential. The change in pressure, if you guys remember, is 9,900,000 Newton per meter square. So 9,900,000 Newton per meter squared times the molar volume, which we have to be 7.0926 times 10 to the power of negative 6 meter cube per mole. Perfect. So, of course, you cancel out meter square from here. You move from meter cube for what you just end up with is just meter and then meter per mole. And then, of course, you put 9,900,000 times 7.0926 times 10 to the power of negative 6. When you input this information in your calculator, you end up getting the change in chemical potential to be 70.21674 Newton meter divided by mole. And remember, Newton meter is the same thing as joules because it's a formula, force times distance. And that is just basically the formula for work done, aka energy. Anyways, Newton times meter or Newton meter is the same thing as joules. So you can just simply say the change in chemical potential is 70.21674 joule per mole. But our work is still not done because we are chemists, so we do not like to keep too much of rough information. So the best thing right here that you're going to do is to put it in the proper number of significant figures or whatever it is that you've been told to do by your teacher. So maybe if you say do this in like 3 sig figs, 5 6 figs, 2 decimal places, whatever the case is, I'm looking at the question and the lowest number of significant figures is 2, right? We have 3 sig figs here, we have 2 sig figs here, we have 4 sig figs here. So I'm going to put this question, or sorry, our final answer in 2 sig figs. So the change in chemical potential is going to be 70 joule per mole. So this is the final answer to this question. I wish you guys all the very best. If you have any questions, please do not forget to ask it. Put it at the bottom of the comment section. If you would like me to be your personal tutor, I tutor students in middle school, high school, and college in order for them to succeed in all their STEM related courses. So if you would want me to tutor you all through college or whether it's even test prep, email me at shuhabitutoring@gmail.com. I wish you all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.